We often use models to predict numbers, things like the price of a house or tomorrow's temperature. But what about questions that aren't numbers at all? What about simple yes or no questions?
How do we build a model that predicts if a customer will cancel their subscription, or if an email is spam? These are binary choices, a simple yes or no. And that straight line we know from linear regression, well, it just doesn't work for this.
By the end of this quick explainer, you'll understand the clever shift in thinking that allows us to solve this, and how we can predict these kinds of binary outcomes by focusing on probability.
So here's how we're going to break it down. First, we'll look at why a straight line is the wrong tool for the job. Then we'll get to the key insight about predicting probability. We'll meet the S-shaped curve that makes it all possible, see where this is used in the real world, and then wrap it all up with one core idea.
So let's start with the problem. Why can't we just use a tool we already have, like linear regression, for a yes-no question?
Well, it comes down to a fundamental mismatch. You see, linear regression is designed to predict a continuous value, a number that can be anything, like a price. But for our problem, we only have two possible outcomes, yes or no. We can think of them as 1 and 0.
If you try to force a straight line to fit these zeros and ones, the line will just keep going. It'll eventually predict values like 1.5 or even negative 0.2. And what does a 150% probability of yes even mean, or a negative 20% chance? It's completely nonsensical. We need a better approach.
And that brings us to the core insight. The solution isn't about forcing the model to work differently. It's about changing the question we're asking it to answer.
And here is that breakthrough idea. We're going to stop trying to predict the outcome directly. Instead, we're going to predict the probability of the outcome. We're asking the model, what is the chance that the answer is yes? And the output should be a number between 0 and 1.
So think of it like this. First, a linear model inside our system calculates a raw score. This score can be any number, positive or negative, big or small. Then we pass that score into a special converter function. This function's only job is to take that raw score and gently squash it into a value that's guaranteed to be between 0 and 1. And that final squashed number, that's our probability.
Okay, so that special converter function we just talked about, it has a proper name, and it's really the technical engine that drives this whole process.
It's called the sigmoid function, and it produces this beautiful, characteristic S-shaped curve. It's a mathematical tool designed to do exactly what we need: take any real number as input and map it perfectly to a value between 0 and 1.
So, we have a probability now, but we still need a final yes or no. How do we get there? We just set a simple decision boundary, or a threshold. Typically, it's set at 0.5. If the model's probability is greater than 0.5, we classify it as a yes or 1. If it's less, we classify it as a no or 0. It's that simple.
So let's just quickly recap the key technical differences. Linear regression gives you a continuous value, while logistic regression gives you a probability between 0 and 1. Linear uses a straight line, logistic uses that S-shaped sigmoid curve. They are just fundamentally different tools for different kinds of problems.
Now, this isn't just some abstract theory. Logistic regression is one of the most practical and widely used algorithms out there. Let's look at where you've probably already seen it in action today.
Ever wonder how your inbox knows which emails are spam? Or how your bank instantly flags a suspicious transaction? Yep, that's often logistic regression. It's also a workhorse in medical diagnostics for predicting disease risk, and in business for figuring out which customers are likely to leave.
To make this really concrete, let's say a model outputs this one single number for some event.
So for a bank's fraud detection system, this could be the calculated probability that a recent transaction is fraudulent. Since 0.92 is way above our 0.5 threshold, the system would immediately flag that transaction, maybe even send you an alert. That's logistic regression working in the background. So why do engineers and data scientists love this algorithm so much? Because it's simple, it's fast, and it's highly interpretable, meaning you can actually look inside and understand why it made a certain prediction. It's an absolutely essential and powerful baseline for any classification problem. Okay, let's bring this all home. If you only remember one thing from this explainer, let this be it.
Logistic regression is a classification algorithm. It works by predicting the probability of a binary outcome, and it does that by mapping a linear model's output through an S-shaped curve.
Or to put it even more simply, don't fit a line to a choice, fit a curve to a probability. And that leaves us with a really important final question.
In a situation where the cost of a mistake is really high, like in a medical diagnosis, is that default 0.5 threshold really the best choice? That's something to think about.